Assalamu alaikum dear students. This is lab number 5. It is a continuation of what we were doing in last lab. We are going to model control systems in Simulink. So first of all, in last lab we already have discussed this command LTI system block in the control system toolbox. And you can use any command, transfer function, zero pole gain or any other. We have not explored SS yet, so we stick on to TF and zero pole gain for now. But we can also use the basic blocks of Similinks, that is differentiator, when we have to implement the terms involving S, integrator when we are using 1 by S, the summer and the gain blocks. First example is done for your convenience here. We have been given transfer function, a very simple transfer function, 3s over s plus 1. And it can be defined in various ways, but the first thing, the easiest thing is use the LTI system block in your Simulink. And the next is we can implement it using the blocks of differentiator, integrator, summer and the gain block. And how can we end up in this? The input going through the derivative block multiplied with 3, then added with the output passing through a derivative block. This is the implementation of 3s over s plus 1 using these individual blocks, and then we have to compare the two results using scope. So I will now explain how we... Okay, so students, we have the transfer function as 3s over s plus 1, right? So we can write it as 3s over s plus 1 is equals to y, the output, by the input u. We'll do a little maths here. We have to cross multiply these two, and once we cross multiply them, we will have y being multiplied with s plus 1 equals to 3s multiplied by u, right? So u is input and y is output. If we multiply these two terms, it will be s into y plus y once and 3s into u. All right. To make it a little simpler, if I have to keep output y, which is single and has nothing with it, the constant y output with no other things being multiplied to it, I can write it as 3s into the input minus s into y. So this is my output equation, right? What I can do is I can simplify, I can just make a block diagram of this control system in which we have one input u and one output y. All right. So I have to take y and create this term s into y. So s into y would be, multiplying s with any term is same as a derivative, and multiplying any term with 1 by s is same as an integrator block. So I can take a derivative block d by dt, it is available in the Simulink library, and pass my output y from this block. The second term that I need is 3s into u, which means the input u has to be multiplied with a factor of 3, which means gain of 3, and then it is to be multiplied with s, which means another derivative block, d by dt. All right. Now these two terms have to be added in such a way that this is plus and this is minus. So I can take this result and use a block with this signs list as plus and minus on these branches. So this, all of this is going to give me y, the final output y. So this means that y of s multiplied passing through a block of derivative is being subtracted with u of s with a gain of 3 and pass on with a block of derivative and a sign of addition here. So this is same as implementing the transfer function 3s over s plus 1. So we can use an LTI system block just like in lab number 4 of your manual and last lab of this semester that you have done in the in your first week. You can give any command here, zero pole gain or TF command or anything, and implement the same and compare the two results by using a scope. Okay, continuing with the lab further, the other task is the direct form 1 realization and direct form 2 realization. You might have done something similar to this in your digital signal processing course. If we have a transfer function written in this formation, the polynomials in the numerator and the polynomials in the denominator, what we can do is we can write them in the form of zeros and poles separately. So the terms in the numerator, they constitute the zeros, and the terms in the denominator, they constitute the poles. So what we can do is that we have to make the first term in the denominator pole equals to 1, for which we are dividing all these terms with s raised to power 3. So it makes it a1 by s, a2 by s square, and a3 by s cube. And we have to make the first term in the numerator free of the variable s. So we are also dividing all the terms in the numerator by s cube. So this results this results into the equation written in step number 2, which means that we can realize or identify these two terms separately, the first one being zeros and the other ones being written as 1 over 1 plus something, which means the poles can be realized from here. S, which means that x of s over y of s. So what we can do is we can make one branch, x of s at the extreme left and y of s, that is the output, at extreme right, and implement this formation. Input being multiplied with b naught, input being multiplied with 1 by b1 and then 1 by s. It means that after passing it through a block of integrator, this is 1 by s, the delay block or the integrator, then it is being multiplied with a coefficient b1 and it has to be added with the previous result. So b naught plus b1 by s is made here at this point. So keep on doing this further for the terms b2 and b3, and this will result into the numerator terms being implemented. What about the terms that are written 1 over 1 plus s? It means that we have to implement the feedback system here. So 1 over 1 plus s means that we have to feed back the output, pass it from the integrator blocks and multiply them with the coefficients. And in the feedback it has to be subtracted. So this is going to be added with minus a1, minus a2 and minus a3. This is extended up to n branches. It can be of any order. But if we implement the poles first and then the zeros, if we implement the poles first, which means that if we implement this side of the equation first, this term of the equation first, it means that first of all we have 1, so we have to pass on x of s as it is. Then we have a1 over s, it means that we have to use an integrator block, that is 1 by s, and multiply it with minus a1 because it is in the feedback system, and then add this into the previous result. Similarly, pass it from another integrator block to make it 1 by s square and pass it with and multiply it with minus a2. and you can increase it up to the number of order that you have in your any given transfer function. And then after implementing 1 over 1 plus the zeros formation, if we move on to implement b naught plus b1 by s plus b2 by s, after observing it a bit, I'm sorry for the dark image that it has, but these are 1 by s blocks. What we can do is we can shorten the expense of the resources by using one block of delay here instead of these two, because the function is same. So this is done here in the second part of the picture. So now the delay blocks or the blocks of integrator 1 by s are reduced, but the implementation is same. So this is called the direct form 2 realization. So your first task is that you have to define these problems. These problems are from your book, and you have to define them in MATLAB using the direct form 1. And of course, the first example that I have explained by using the summer, integrators, and differentiator blocks. The other task is that you have to define the system given in Simulink using the direct form 2 realization. And for direct form 2 realization, what you are required to do, you have to define DC motor position system. And for DC motor position system, here the values are given. This is the transfer function, and these are the values of the coefficients and constants in this transfer function. So first feed these values, generate this transfer function, and then implement the same in Simulink using the direct form 2 realization.